Okay, a very good morning to all of you. Today we are going to learn the surface integral of vector field, or called as the flux integral. After you have learned the surface integral of scalar field, okay, as a mass of a lamina in 3D space. So let's consider a steady state flow and incompressible fluid. Okay? Steady flow means velocity of the fluid does not vary with time. Incompressible fluid means the fluid has a uniform density and cannot be altered by compressive force. So you have a fluid with velocity f passing through a small this is a space S, now passing through a small space S with unit normal vector n, from the space S. Then let the vector f as usual as mi plus nj plus pk be the velocity field. F is actually the velocity field of the fluid. Let S be an oriented space. Then we divide the space S into n parts. Consider the I part. Consider a small part, as in the picture here. We have a space S, and then we have a fluid with velocity F passing through. Let's say this is a small part of the space S here, a small portion of the space S. So a small portion of the surface S, delta Si, and the volume of fluid passes through a unit space, delta Si, per unit time. The F is a velocity. The units, remember velocity, you have in SI unit, you have the meter per second. This is small unit of space. You have the area S squared. The area is meter squared. So total you have meter cube per second. Meter cube per second means it's the volume of the fluid passes through a a unit delta Si per unit time. That's why it's volume per time. Volume per time passing through a small surface delta Si. Why dot with n? Because the vector field may not diagonal to your diagonal to the surface S. That's why dot with the normal vector from the surface S. So volume of fluid passes through the whole surface S per unit time. It's just like only a small portion of surface S. So if passing through the whole surface S, then you have to sum the small portion of surface S, mean delta Si from I equal to 1 up to n. When n approaches infinity, this becomes the surface integral of vector field, or called as flux integral. Flux integral. Given by double integral f dot n d capital S across surface S. If we call back, if the surface integral of scalar field, this is only the scalar function f x y z. Now this is f dot n, this is a vector, so this is surface integral of vector field, which is also called as flux integral. So the integral that we find here is actually the volume of fluid passes through a surface S per unit time, mean the unit is meter cube per second, is a volume of fluid passes through a surface S per unit time V, also called as flux. Volume of fluid passes through the surface S per unit time is called flux, and this integral also called as flux integral or surface integral of vector field. So this integral called as flux integral of F across surface S. If the flux integral we multiply with a constant density. Remember you have the mass of a solid G, mass of solid G with constant density. Mass will be of density multiplied volume. Since this is a volume per unit time of the fluid passes through the surface S, so if we have here this integral multiplied with density. So this becomes mass of fluid passes through a surface S per unit time. Now this is volume per unit time multiply density. So become mass K per unit time. Mass of fluid passes through a surface S per unit time. Definitions of flux integral. Let the F as usual represented by mi plus nj plus pk, where m and p have continuous first partial derivative on the surface S oriented by a unit normal vector n. In the surface S, have a unit normal vector n. The flux integral of F across S is given by double integral F dot n d. The capital S is a 1 unit of surface area across the surface S. D lowercase s, that is a 1 unit of arc length, what you learn in line integral of scalar field. How to evaluating a unit normal vector n. Let the surface S is given by z equal to gxy. And let capital function of capital G x y z equal to z minus gxy. How to find the unit normal vector? Unit normal vector will be the del G. Del G is actually the normal vector divided by magnitude of the normal vector, so it becomes 1 unit of the normal vector. Where the del is actually, G is a constant scalar function, and del is a differential operator. Differential operator, which is del del xi plus del del gk, del del yj plus del del zk. Once del g become del g del xi plus del g del yj plus del g del zk. Mean actually del is a differential operator. Del is del del xi. Plus you have the del del y j, and then del del zk. This is del differential operator. You multiply with scalar function g, that's why you get del g del xi plus del g del yj plus del g del zk divided by magnitude of del g. So magnitude of a vector, you have a square root, take each component, you square it, plus del g del y squared plus del g del z squared it. And then g, function g actually, g equal to z minus gxy, So del g del x, del g del x means it differentiate g respect to x, once g equal to z equal to g equal to z minus gxy. So del g del x, g respect to x, negative gx, negative gx, negative gx, and because g equal to z, g lowercase g equal to z, so also equal to negative zx. So del g del x equal to negative del z del x. Similarly, del g del y will become negative del z del y. Because if you del g del y, differentiate g here respect to y, this is z. So del g del y we have negative gy, and then g equal to z, so equal to negative zy. So that's why del g del x equal to negative del z del x, del g del y equal to negative del z del y, del g del z, del g del z. Differentiate g here respect to z, you get positive 1. Positive 1, so that's why it's positive 1k. So this is okay for unit normal vector which is oriented upward because okay, component K is positive. Component K it means positive, so your unit normal vector will be pointed up. Okay, if you have a unit normal vector which is oriented downward, okay, component K negative, component I and J become positive, means opposite direction of the unit normal vector which is pointing up. Pointing up, K positive, component I negative, component J negative. If pointing downward, okay, component I here positive, component J here positive, component K negative. Okay. So to evaluate the flux integral, so we have the F dot, the N is a unit normal vector. Okay, for N pointing up, your unit normal vector is negative del Z del Xi minus del Z del Yj plus positive K. Okay, numerator here is the normal vector. You want unit normal vector, so divided by the magnitude of the normal vector, which is square root of, you take component I, you square it, component J, you square it, component K, you square it. Okay, ds, this is formula of 1 unit of surface area, as you learn in surface integral of scalar field or surface area of double integral. The 1 unit of surface area is square root of del z del x squared plus del z del y squared plus 1 dA. So across surface S, now the surface S, you project it become region R. Region R. So and square root and both square root cancel out. That's why to evaluate the flux integral, if the unit normal vector is pointing up, the left up with the double integral F dot. This is actually normal vector dA, which is pointing up, oriented upward. Then F dot negative del Z del Xi minus del Z del Yj plus K dA over region R, the surface S. Okay, you press it, you get the projections on the XY plane, so that then you get your region R. This is for. Then for the unit normal vector, which is pointing down, once you simplify, you get this positive I, positive J, this negative K. Okay, but here you can go through the derivation. Okay, for flux integral which with surface has a unit normal vector pointing down. Okay, so your unit normal vector, the normal vector here, component I positive, component J positive, component K negative. You take square root here, same, and then this is a ds. Still you get the same formula, square root zx squared plus zy squared. So both square root you cancel. So you get this is flux integral where the surface has a unit normal vector oriented downward, F dot. So how you know this is up or down? Look at the component K. If component K negative means Z negative, so this surface has a unit normal vector pointing down. So if K positive, the other negative, that is oriented upward. Then example 1, we have 3 examples to demonstrate how you evaluate the flux integral. Let S be a surface Z equal to 1 minus x squared minus y squared that lie above the xy plane. This is a paraboloid surface line above, bounded from Z0 until the parabolic surface with the maximum point at Z equal to 1. Oriented by an upward unit normal vector. We have an upward unit normal vector. Then you should evaluate your flux integral using this formula, F dot the normal vector dA over region R. Region R for this surface, if press it, will be on xy plane. Find the flux of the flow field F xyz equal to xi plus yj plus zk. So you must understand flux is actually given by the flux integral. The flux integral, this is a flux. Surface integral of vector field F dot n d capital S over surface S. And then first of all, because the question said the unit normal vector is pointing up, so your unit normal vector is negative del z del xi minus del z del yj plus k divided by magnitude of the normal vector, which is square root del z del x squared plus del z del y squared plus 1. Okay, this is formula for one unit of surface area of your paraboloid or any surface which is given by z equal to gxy. So the square root and square root here cancel. Then you have f dot negative del z del xi negative del z del yj plus k dA over region R. Okay, plug in the vector field. Okay, f given is xi plus yj plus zk dot v. Okay, so you need to find your del z del x del z del y. Okay, to find del z del x, express the z from the surface as given. Okay, this is in the nice form, z equal to 1 minus x squared minus y squared, hence zx. When you del the del the x del z here, del the x. So del the x1 0, del the x negative x squared, you have negative 2x, del the x negative y squared got 0. So similarly, zy, you del the y each term of z here, del the y 1 0, del the y negative x squared 0, del the y negative y squared got negative 2y. Okay, so zx, zy is negative 2x, negative 2y. So you obtain zx is negative 2x. zy is negative 2y. So negative, negative, so you have positive 2x. Negative, negative, positive 2y, component k1. And then do the dot product first. F dot, the n. So you have x times 2x, 2x squared, and then you have y multiply 2y, 2y squared. Okay, lastly, you have the component k, z multiply the 1, so plus z, dA over region R. Okay, region R, in the paraboloid surface, z equal to 1 minus x squared minus y squared. The region R is on the xy plane, where z equal to 0. If you plug in z equal to 0, then you have 0 equal to 1 minus x squared minus y squared, or x squared plus y squared equal to 1, which is circle with radius 1 unit. Hence, you can solve your dA using polar coordinate, become r dr d theta. Okay, and r will be x squared plus y squared will be your r squared equal to 1. Hence, r is magnitude is always taking positive value. R is 1. So r is actually from origin, which is 0, until touch the curve x squared plus y squared equal to 1, which is r always 0 up to 1. Okay, theta full circle is always theta 0 until theta up to 2 pi, because full circle. We have a full cycle. So r 0 to 1, theta 0 to 2 pi. So mean up to here, it actually becomes this one, the A, change it to polar coordinate, r dr d theta, r from 0 to 1, theta from 0 to 2 pi. Okay, this one we stop here, right? 2x squared plus 2y squared plus z. Okay, now you see we have a double integral, so z, you must be substitute. Z is actually from paraboloid equation, which is z equal to 1 minus x squared minus y squared. Substitute z from the paraboloid equation, which is z equal 1 minus x squared minus y squared. Because double integral, so we have to eliminate z in terms of x and y. So z is the surface given z equal to 1 minus x squared minus y squared. And then you simplify it before you integrate respect to using polar coordinate. 2x squared minus x squared, you have x squared. 2y squared minus y squared got y squared, and then plus 1. Since the region R is a unit circle with radius 1 unit centered at origin, dA, okay, we evaluate it using polar coordinate, which is equal to R dr d theta, R from 0 to 1, theta from 0 to 2 pi. Then we replace x squared plus y squared equal to R squared. So you have R squared plus 1. So total you have R cubed. Integrate R cubed plus R dr. So first term R cubed, so you have R4 over 4. Second term R dr, you have R squared over 2. If you plug in the limit from 0 to 1, you get, okay, here. So you have 1/4 plus half. So become 3 over 4. Then lastly, integrate 1 with theta. Plug in limit from 0 to 2 pi, got 2 pi. So total 2 and 4 cancel, got 3 pi over 2. 3 pi over 2. So the second example, let S be the sphere. X squared plus y squared plus z squared equal to a squared. Oriented outward. Out. In this case, example 1 just now, up. Paraboloid upward, but this is out. Okay? And let F actually equal to ZK. Evaluate the flux integral. Evaluate the flux integral here. Okay, why they call out? Because sphere, for upper hemisphere, oriented out means assume you have a flow inside the sphere flowing out. And for upper hemisphere, okay, it's flowing up. Lower hemisphere will be down because flowing up. Okay, so that's why sphere we have to divide it to two surface. And on the upper hemisphere S1, the outward unit normal vector is upward. Okay, on the lower hemisphere S2, the outward unit normal vector is downward. You have to break the surface into S1 and S2, like what you break, okay, the line integral. If you have a piecewise smooth curve, you break it into several curves. Now, because of sphere, okay, you have two different orientation. For upper hemisphere, unit normal vector is pointing up and out. For lower hemisphere, unit normal vector is, okay, pointing down and out. So you have to break it into two surfaces, because if unit normal vector pointing up, your unit normal vector formula, okay, different with unit normal vector which is pointing down. Okay, if you evaluate each of it, you got the answer 2 pi a cubed over 3. 2 pi a cubed over 3, add up, we have 4 pi a cubed over 3. Later on, we are going to look through how we get the flux integral on surface S1, S2, which is upper hemisphere and lower hemisphere. Okay, let the upper hemisphere is S1. So S1, okay, from the sphere, okay, equation, x squared plus y squared plus z squared. If you make z as a title, you have z equal to positive, negative, third a squared minus x squared minus y squared. So for upper hemisphere, z is positive. For lower hemisphere, z is negative. Okay, and then to evaluate the unit normal vector, we need the zx, zy. Okay, square root is actually power half. So to find del z, del x, okay, for differentiation, you bring power, okay, in front, power half, and then, okay, your power half here, square root is actually you have power half. For differentiations, power become multiplication half, and then you have a squared minus x squared minus y squared for differentiation. So you minus with power with 1. Integration, it plus 1. So half minus 1, that's why it become power negative half. Later on, you del x, a squared minus x squared minus y squared, that's why you get negative 2x. Okay, 2, you cancel. So you left numerator negative x. So power negative half is actually become divide square root a squared minus x squared minus y squared. Similarly, for zy is only this part because you need to del y a squared minus x squared minus y squared, get negative 2y. And then you get negative y over sub a squared minus x squared minus y squared. So the flux integral on surface S1, which is upper hemisphere. So unit normal vector pointing up, so is the normal vector, this negative del z del xi, negative del z del yj plus k. The positive, the square root. This one is from ds. Numerator here, this is normal vector pointing up. You want unit normal vector, so divide by magnitude of the normal vector. And magnitude of normal vector, the formula is same is ds, so cancel out. So you have f dot normal vector dA over region R. The f is actually consists of component k, zk. So dot with del z del x, negative del z del x. Del z del x will have negative, and that negative again, that's why you have positive x. Now positive x over sub a squared minus x squared minus y squared. Similarly with negative del z del y. Del z del y initially have negative y. This one type. This is y. Del z del y, you have negative y sub a squared minus x squared minus y squared multiplied with negative, so become positive. The component k is 1. And then when you do the dot product, component I 0 to anything 0, component j 0 to anything 0, you just left component z times 1. To become double integral z dA over region R. The region R is your region R is here. In the upper hemisphere or lower hemisphere, the region R happens when z equal to 0. So you have circle x squared plus y squared equal to a squared. So R is actually equal to a. The sketching, because we use a mapper, you cannot put a, we put 1 unit here. So your R is actually from origin 0 until the radius of the circle, which is a, theta. Theta from 0 until theta equal to 2 pi. So that's why R is actually 0 to a, theta 0 to 2 pi. And then this is factor out negative. So you have x squared plus y squared, which is r squared. So become integral of sub a squared minus r squared. dA change to polar coordinate become r dr d theta. And you can evaluate this integral using substitution technique, where you let u equal to a squared minus r squared. So du is negative 2r dr. Notice you want r dr. You want r dr. So it become du over negative 2. Hence the integral of sub a squared minus r squared r dr replaced by du over negative 2. And then the sub a squared minus r squared become u power half. Integrate u power half become u power 3 over 2 divided by 3 over 2. So you cancel the 2 here. So become negative u power 3 over 2 divided by 3. Replace back the u is actually a squared minus r squared. Power 3 over 2 divided by negative 3. So that's why here you get the result of this integral is negative 1/3 a squared minus r squared power 3 over 2, where the r from 0 to a, d theta from 0 to 2 pi. So remember, you integrate respect to r, substitute your limit into r. So a squared minus a squared have 0. Later on, minus substitution of lower limit into r. Okay, this is 0, so you have a squared power 3 over 2, so it cancel. So become negative, negative cancel, become a power 3 over 3. And then lastly, integrate 1 the theta from 0 to 2 pi, you get 2 pi. That's why the answer 2 pi a cubed over 3. This for surface S1, which is upper hemisphere. Upper hemisphere. Okay, for the lower hemisphere, the difference is z is negative. So a squared minus x squared minus y squared, and then you find the zx, because initially negative. So square root is power half. Okay, and then for differentiation, power half minus 1 minus half, and then you del x inside the square root, you get negative 2x. So negative, negative here cancel. So you got positive x compared to just now. For S1, zx you get negative, positive x over sub a squared minus x squared minus y squared. Similarly, zy is only here is negative 2y. So simplify, you get y over sub a squared minus x squared minus y squared. Then the flux integral f dot n ds, the difference here, n is pointing down, that's why normal vector, component I positive, component j positive, component k negative. Okay, similar with pointing down just now, square root, pointing up just now. Okay, this is the magnitude of the normal vector. Okay, another, this square root is actually ds. So square root and square root here cancel each other. So you get this is flux integral if the unit normal vector pointing down. So notice component k negative. If pointing up, component k positive, the other two component negative. So plug in, okay, the f is only zk dot with your del z del x. Okay, del z del x in this case positive, del z del x positive x over the square root zy positive y over the square root there. So that's why you get this. So the component k is negative 1. So 0 times this k 1 you get 0. 0 times this one you get 0. So only left z times negative 1. So which is negative z. Okay. For S2, z is negative. For surface 2, S2 is lower hemisphere, z negative. So negative, negative, positive. So again, you see for both S1 and S2, lastly you arrive at the same integral. The same integral. Yeah. You get with the same integral. That's why the result you have the same, okay, 2 pi a cubed over 3. Because it arrived at the same integral where you factor out negative. So square root a squared minus r squared, r dr, is quite exactly the same as the previous case, surface S1, in the same integral. So you should get the same result, 2 pi a cubed over 3. That's why for sphere, you have to do it 2 times. You break it as surface S1 and S2. For surface S1, you get 2 pi a cubed over 3. Surface S2 also 2 pi a cubed over 3 because, okay, after we carry on, we arrive at this step, the same integral. So we get the same result, 2 pi a cubed over 3. So this is the second example. You notice sphere, you have to divide it into the upper hemisphere because the unit normal vector pointing up, lower hemisphere because unit normal vector pointing down. You have to evaluate the flux integral 2 times. Okay, now the last example. S is a surface of the cube bounded by the planes x equal to 0, x equal to 1, y equal 0, y equal 1, z0, z1 oriented outward. Similar with example 2 of the sphere, oriented out. Assume the water or the fluid flowing out. At each surface, they have a different direction. The sphere, upper hemisphere pointing up. Lower hemisphere pointing down, but here the cube, each surface different direction of a unit normal vector. Then find the flux of the vector field F equal to 2xi plus 3yj plus z squared k across S. Across S. So we have actually unit cube. Okay. front here is x1, at the back, okay, or at the zy plane is x0. At the xy plane is z0, on top surface is z1, at the zx plane is y0, okay, here is a y equal to 1, unit cube. So you have 6 surface. You have to break your flux integral, you have to do your flux integral 6 times. Each of it you got, okay, the answer, add up you got total answer is 6, but you have to do it 6 times. Okay, and we are going to look through the result for each surface. Let the S1 is a plane z equals 0, okay, on xy plane, and the water flow out. That's why the unit normal vector, which is okay, diagonal or orthogonal with z equal to 0 will be negative k. Because on z0, normal vector, which is positive, flow out, and orthogonal to z0 is negative k only. Then this is a vector f given, and you do the dot product, it only consists of, because these two components 0, so you get negative z squared, and surface S1 is actually z0, so integrate 0, you got answer 0. That's right. For S1, the flux integral you get 0. Okay. Later on, S2 is a plane z1, and water flow out. So the unit normal vector is positive 1. So normal vector which is parallel with z axis flowing out from z equal to 1 is positive k. Once, okay, doing your dot product, you have this is positive z squared dA, because this one 2x times 0, you got 0, 2y times 0, you got 0, and left z squared times 1, which is z squared. Surface S2 z equal to 1. So you have a double integral dA over region R. Okay, this is actually on surface S2, because you have unit cube. Each of the surface, and you got 6 surfaces. Each of the surface, the area is actually 1 unit. Because this represents the area of surface S2, which is equal to 1 unit. Because what you have is unit cube. Yeah. Each surface, their area is 1 unit. Then you get this one. This double integral is actually represent the area of S2, which is 1 unit. S2, the projection you get is on z equal to 0. But each surface you have 1 unit. That's why here this actually represent the area of surface S2, which is 1. Okay, that's why the second result you have 1 here. Okay, S3 with the plane y equal to 0. Y0. Okay, Y0 is on the zx plane. And then your unit normal vector parallel with the y-axis flowing out. That's why it is negative j. Okay, s equal to 0. Okay, your unit normal vector here, which is for z0 unit normal vector pointing up, so it's a positive k. Okay, and then if z0 unit normal vector pointing up, because flowing out of the positive k, z0 will be negative k. For y0, pointing out here, so which is negative j. So if this one will be positive j. So if x equal to 1, pointing out here, which is positive I. Okay, at the back there, you're pointing, this one will be negative I. So that's why for S3, plane y equal to 0, y0 at the zx plane, and the flux flowing out, so unit normal vector, which is parallel with our y-axis, is negative j. Okay, evaluate the dot product, you have only 3y times negative 1, so negative 3y. Surface S3 is y0. So that's why you get the result is 0. That's why the third one, the result is 0. Then surface S4 will be on y equal to 1. Y equal to 1, unit normal vector, okay, parallel with a positive y direction, which is positive j, because flux flowing out from the plane y equal to 1. From the plane y equal to 1. So flowing out here, so it's positive j. So S4, positive j. Okay, so the dot product, you have only left 3y. Double integral 3y dA. Okay, on surface S4, y is 1. That's why you got 3 times double integral dA over region 4, which represent the area of surface S4, because you have each unit cube, so each surface is 1 unit. That's why this double integral represent 1. Okay, that's why you got answer is 3. Yeah, the plot is 3. So the S phi is on x equal to 0. Surface S phi on S equal to 0. S equal to 0. Okay, is on the ZY plane. The S phi is on, x0 is on ZY plane. So the flux flowing out and parallel with the ZY plane, okay, the unit normal vector is negative I. Negative I. So for your S number 5, unit normal vector is negative I, hence the dot product you get here is negative 2x. Okay, however, on S phi x is 0. That's why your flux integral you get 0. So notice S1 0 because Z0, S3 0 because Y0, S5 0 because X0. Okay, lastly, S6 is on the plane x equal to 1. X equal to 1, the water flow out. So the unit normal vector orthogonal with the plane x equal to 1 is positive I. Positive I. As you see here, this is plane x equal to 1. Okay, water flow out. So unit normal vector orthogonal with the plane x equal to 1 will be in the positive x direction, which is positive I. Okay, this is positive I. Then you do the dot product on S6, the dot product, you get only 2x. Okay, and on surface S6, x equal to 1. So you got 2 times double integral. Okay, dA, this represents the area of S6, which is equal to 1. That's why answer is 2. So add up, total 1 plus 3 plus 2 is 6. So in this case, lectures we have gone through the flux integral or surface integral of vector field. Okay, which represent the flux. Okay, actually, this is a flux integral or surface integral of vector field because f dot n here is vector, not a scalar function. Okay, if scalar function, that become the surface integral of scalar field, represent the mass of lamina in 3D space. So if your integrand here is vector f dot n, this represents the flux. The flux is actually volume of fluid passes through the surface S per unit time. This is called the flux, and floating we call flux integral of F across surface S. Cos of F is velocity field. You have the unit is actually meter per second. ds is 1 unit of the surface area. So meter squared total meter cube per second. So become volume of fluid passes through the surface S per unit time. We call it flux. Mean how much of the volume of fluid passes through the surface S per unit time. So this is what we call flux integral. Okay, if your flux integral multiply with your constant density, this becomes the mass of fluid passes through a surface S per unit time. Because mass of the solid will be density times the volume. Since this is the volume per unit time, so this is the mass of fluid passes through a surface S per unit of time. Okay, and then how you evaluate the flux integral? This will go to the F dot n ds. Okay, F dot n ds. So unit normal vector is pointing up. Okay, numerator here, this is a normal vector which is pointing up. So component K positive, because pointing up is actually parallel with positive z-axis. Component I is negative, component J is negative. We want n is 1 unit of normal vector, so divided by magnitude of the normal vector, which is square root del z del x squared plus del z. This is del z del y. So del z del y squared plus 1. Okay, this is a ds, 1 unit of surface area, as you learned in the surface integral of scalar field. ds is square root del z del x squared plus del z del y squared plus 1, or similar to the surface area in double integral. So the square root and square root cancel. So left, okay, double integral f dot negative del z del xi negative del z del yj plus k dA for unit normal vector which is oriented upward. Okay, if unit normal vector pointing down, you notice, okay, normal vector which is pointing down, so component K negative pointing down. So to be parallel with negative z-axis. So component I positive, component J positive. This is magnitude of a normal vector. This is a ds, square root cancel. We have the f dot negative and f dot positive del z del xi plus del z del yj minus k for unit normal vector which is oriented downward. Okay, and then to get the del z del x, identify your surface. Okay, express it as a z, as a title. Okay, and then we've gone through 3 examples. Example 1, okay, you got this is a z paraboloid. Then, okay, already said pointing upward. Then you use this formula. So plug in the f. Then you just need to find your, from z you find your del z del x, del z del y, using it, and okay, oriented upward. Then you use this formula. Okay, from the surface parabolic z there, find your del z del x, del z del y. Evaluate your dot product first. Later on become double integral dA over region R. To get dA over region R from the surface, let z0, then we'll get your region R. So in this case, region R is circular, then you solve it using polar coordinate. Okay, and for sphere, second example, because we have a 2 different unit normal vector. Upper hemisphere, unit normal vector is upward. Okay, lower hemisphere, unit normal vector is downward. So you have to break the surface into S1 and S2. S1 and S2, and that means you will use these 2 formula. Okay, S1, you have this formula. Okay, S2, another formula, and combine it. And then the third example is a cube. Because cube, we don't have the exact as a title. And cube, we have the 6 surface. 6 surface. So you have to do your flux integral 6 times. 6 times. 6 times. However, for your unit normal vector, okay, you don't need the formula, okay, negative del z del x, because we don't have the z as a title, but we know, okay, the unit normal vector for cube, okay, on top surface, with the flux flowing outward top surface, unit normal vector will be positive k. Positive k. Okay, bottom surface, unit normal vector, negative k. Unit normal vector, okay, means orthogonal with the surface. Top surface, positive k, down bottom surface, negative k. Okay, and then for this one, plane, this is plane x equal to 1, unit normal vector flowing out, which is positive I. So at the back will be negative I. For y equal to 1, unit normal vector flowing out with positive j. Okay, at the zx plane, that will be negative j. Then you do it 6 times to get the answer. Okay, so with this, okay, you conclude back what you have learned in the flux integral or surface integral of vector field. Okay, and thank you for your attention and watching this video.